Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are Himadri Majumdar, CEO and co-founder of Semiqon, and Janne Lehtinen, CSO of Semiqon. Himadri, Janne, and I talk about Semiqon's silicon spin-qubits technology, their unique ways of shortening fab cycle time, the expected specs of their first machine, and much more. We hope you enjoyed this episode. Hello, Himadri. Hello, Janne. Thank you so much for joining me today.
Thank you for having us.
Thank you. So who are you and what do you do?
Yeah, so maybe I start. My name is Himadri Majumdar, and I'm the chief executive of a up-and-coming spin-off from VTT called Semiqon with a Q. And today we will be talking about that. And before I joined Semiqon, I was the program manager for quantum technologies at VTT, which is a technical research center in Finland. And in that role, led various initiatives in quantum tech for the last couple of years, but now full-time in Semiqon, leading the company.
And I'm Janne Lehtinen, Chief Science Officer of Semiqon. I was a research team leader at VTT before joining Semiqon. I've got background roughly 10 years of superconducting quantum technology and now 5 years of semiconductors. And you see where I'm now, so where I'm thinking that the future will be, so semiconductors.
Excellent. So what modality does Semiqon use?
Modality?
In terms of what are the platforms?
Oh, right.
Yes.
Yeah. So we are using silicon spin qubits. So our target is to do whole spin qubits that operate at elevated temperatures. So elevated here means a little bit above 1 Kelvin. So still requires cryostat, but the power budget that's available for our qubit systems is significantly higher than in the millikelvin regime. So.
And what is the advantage of spin qubits over semiconductors or trapped ions or other quantum modalities?
Okay, the advantage, there are several. So let's start with the first one, and that's just the physical size of the qubits. So currently, if you compare, for example, with the superconductors, you have something which is 200 micron sized qubit roughly. And on semiconductors, you can go by factor 1,000 smaller, so something like 100 to 200 nanometer per qubit in size. And this, of course, enables scalability in sense that you can back then more of these qubits on your chip. And then the second thing is that we have really well-established fabrication technology. So of course, all our traditional hardware that's based on silicon processing. And now we can leverage this to make these high-quality components for silicon quantum processors also. And then, which we already a little bit scraped there, was the operation temperature. So these silicon qubits can be operated up to temperature of several kelvins, which then enables monolithic integration. So we can put control hardware in addition to the qubits on the same chip. And this relaxes a lot of the infrastructure which you need for your QPU. So in the end, you could actually make a QPU in sense that you can just have digital in, digital out kind of operation. It functions as real processor, not just qubits and the classical processor outside.
Right. So we are talking about quantum IC here, quantum integrated circuits, so to speak.
Aren't there other companies that are using spin qubits?
Yes, of course. I mean, we are not the only company doing it. Otherwise, you can ask the question, why are you the only company doing it? No, there are, of course, competition. And the biggest and the most recognized would be Intel trying to do it based on their ostrich processors and so on. And then, of course, there are competition in UK, in France, in Australia as well. But what we see it is we don't necessarily see them as competition as such. We see it as potential collaborators, because our business model as a company is not to become a full stack quantum computer maker. We want to focus on the processors and build the best processors that there are. So if all goes well, we might hold the best processors that there can be based on semiconductor spin qubits, and the other companies can potentially become our customers or partners as well. Because what we want to see is we are the best in the processors, and then others who are doing the system integration, they are good at that. So we don't want to do their job for them. So we want to build partnerships, we want to build collaboration, and then address the, let's say, the million qubit era, hopefully in the future, building the best quantum computers there can be with our processors. So that's kind of like our big goal, so to speak.
I think you mentioned that you're a spin-off from VTT.
Correct.
I believe that VTT, and perhaps you, while you were working at VTT, made some exciting demonstrations of spin qubits. Could you give us the highlights of what these demonstrations were? What were the achievements that you were able to show?
Yeah, so what we did at VTT was establish fabrication platform for these quantum dot-based devices. And we demonstrated that we can have several of these quantum dot arrays embedded in a cryomultiplexer. So we monolithically integrated the quantum dots to kind of classical CMOS, which is the cryomultiplexer. So that kind of showcases the possibility of extending these kind of systems to large-scale processor units. And now what we are going to do is to operate these quantum dots as spin qubits. So the quantum dots are kind of pre-stage of the qubit. And that's the current technology level. But what we are aiming is to be able to do solutions that truly scale, and that's why we take these steps by step. So first we need to be able to do the best quantum dots, and then we can make the best spin qubits.
Right. So you guys have already demonstrated one of the best possible low charge noise devices that there are in terms of quantum dots.
Yeah, the charge noises which we measured have been always at elevated temperatures, since that's our temperature that we want to operate our spin qubits. So the target is to be there and still have sufficiently good systems.
Right.
Building quantum hardware takes time. I'm guessing. How long do you anticipate before you have something to show the market from Semiqon, from the new company?
Janne can answer the technical side, but what our investors would like to see is one of the things that we actually are hoping we are very good at is to have a very fast design and fabrication cycle, which allows us to do the development quicker and get to the next generation faster and faster. So from our perspective, what we want to do is in a 2-year time frame go beyond the state of the art that exists right now, and then have different milestones in terms of tens and hundreds going forward as we continue the journey. But Janne, if you want to add some more details to that.
Yeah, I think that's the key message. So what we are doing is to compress the fabrication cycle in 2 months that typically take, let's say, up to 9 months or so in the CMOS. So this is the thing, and then we can iterate fast and develop fast these processors. And of course, the concrete demonstrators that we are aiming, those will be similar to what's already done, but we do it in a way that there are no hero devices. We do it on vapor scale and characterize the devices on vapor scale to see that we have good yields and we can actually produce the processors on quantities that are sufficient.
Yeah, and in that respect, one thing that your audience might be interested in is most of the spin qubit devices based on CMOS are very much dependent on the fab. So all the companies who are trying it either are doing it using their existing large fabs or doing it in university fabs. But what we have as an advantage, so to speak, is we are operating out of this, let's say, infrastructure or clean room, which is pilot line, basically, at VTT. So we have full access and full operational capacity in that clean room. So that allows us to not just do early level prototype and devices, but go to the pilot scale already by ourselves. So that's a huge advantage in terms of delivering the targets quicker as well.
Does that mean you anticipate that the pilots or the initial products will be manufactured at VTT, and only later, when you go to even larger scale, you will engage in external fab?
In a way, just to correct that, so the fab that we are talking about is a let's say, accessible to all end users. So we will be the one doing it in the fab, even though the fab is owned by VTT and the universities. But we will be the operating unit in the fab. And yes, then you are correct that we will be doing the pilot manufacturing and the first generation of products in that fab. And then when it scales and the volume goes higher, then we will have tech transfer and partnerships accordingly. That's correct.
Some hardware companies are building application-specific computers. They say, well, we can design the chip to fit a particular type of optimization problem, or maybe we do something for machine learning and so on. Do you envision your machine to be general purpose, universal quantum, or do you envision it to be tailored to a specific type of application?
Well, the target is general purpose computer, but of course there are specific things which you could address with the spin qubits better. So it's it's a really broad question to ask, but the target is on the general side.
Yeah, and what I think we can also quite easily say is being on the early stage of the company, we are quite open to collaboration. So within your audience, if there are university and research groups who want to try out a certain kind of device, then we are open to those kind of suggestions and options. And but like Janne said, our target is to go for general purpose, but we know we will have different milestones going forward in the early stages, for sure.
If you can share, how large in terms of number of qubits do you expect the initial device to be? How fast is the cycle time or the clock rate? Any specs you can share on your initial goals?
Initially, well, the size will be, let's say, 2 to 6 qubits at first. And the state of the art is currently 6 qubits, so that's already there. These will be really fast as all qubits, so the gate speeds will be really large. But then of course we cannot too much say about the other performance factors, since we haven't yet done spin qubit experiments with our quantum dots. But the target is, of course, that we get there to the state-of-the-art results. So having some microsecond coherence times and so on for these qubits.
How large is the company, and how large do you expect it to become in the next couple of years?
Yeah, very good question. Because based on this, our strategy of being a very core quantum processor company, we started with a small team of core founders and employees. So we will be 5 starting with. And then in the next couple of years, we will most likely grow by 1 or 2 employees more, depending on the strategic, let's say, employees that we will hire. And even further beyond that, we won't be growing exponentially because we know we have a task to fulfill in terms of developing our designs and doing the demonstration of the first, let's say, tens of qubits in a processor. But after that, depending on how we grow in terms of our revenue and how we grow in terms of our client demand, then we have a scope to grow. But we don't intend to grow unless there is a very clear commercial path ahead of us as well. So we are very mindful of our burn rate, so to speak, as it's called.
That sounds like an incredibly capital efficient company in terms of the number of employees. How are you funded?
Right. So we started operations, and you will the time when your listeners will be hearing this podcast, we will be announcing it, that we have some early stage pre-seed investment from our investors, private investors, and some strategic angel investors. And that would be the starting point for us. But we are, of course, going to have a lot of public-private partnership projects based out of public funds in Europe as well, where we will be participating. And this is how we are going to grow. As I said in the beginning, our goal is to grow in a collaborative manner. So we will work together with other stakeholders in various public-funded projects and concentrate on our product development and then grow from there. So that's kind of like the goal.
What can you share with me about the quantum ecosystem in Finland? Why is Finland a unique place to build a quantum computing company?
Yeah, this is it goes to the core of our existence, basically. So Finland has been very strong, and you can see it from the companies like Blueforce, IQM, for example, that it has been very strong from the fundamental science for decades, and this has led to those companies, Blueforce and IQM, to be successful and operating right now. And it's the same with the technology that Janne was talking about that we have developed at VTT. And it all boils down to years of research and also critical infrastructures, having access to critical infrastructure. So all these factors come together to build the scope for us to be in the right place at the right time. So if you can call it that way. So, and this sort of allows us to also leverage the ecosystem. So having Blueforce close by, providing the best cryogenic solutions in the world, having IQM, who have now developed and built a business, and having sort of partnerships with them and discussions with them. So all these factors, and also companies like Quantrologs, for example, who are providing specific solutions and can potentially be one of our close partners. So all these ecosystem players actually help us, and we hopefully will be helping them as well going forward to build the base. But it's very, very important that the research ecosystem, the education ecosystem, and the infrastructure is here in Finland to allow us to do those things.
As we get close to the end of our conversation, I wanted to ask you both a hypothetical question. If you could have dinner with one of the quantum greats, dead or alive, who would that person be?
Oh, great question. I let Janne answer first while I think.
Yeah, I guess it would be nice to meet the Schrödinger if it would be possible. So, there could be.
And why so? Why Schrödinger?
Well, that's even better question. I don't know. That's the person who kind of I had to deal most in my studies. That's from that side.
I would actually love to meet Professor Feynman, Richard Feynman. He's one of the person who motivated me to study physics, actually. So, and who knows, if I meet him, I would even find some solutions for making better spin qubits, knowing how great he is. So, yeah.
Excellent. So I wish you lots of luck in your journey, and thank you so much for joining me today.
Thank you, Yuval.
Thank you.